This is a video on integration by parts. Integration by parts is used typically when you have the integral of a product of functions. In this case, I'm going to start by showing you where the actual integral comes from and the process comes from, and then we'll do some examples. So suppose that you were taking the derivative with respect to x of a function u times some function v, and u is a function of x and v is also a function of x. Then this would be equal to, right, this is a product here, so if you have the derivative of a product, we have to use product rule. And the way we talk about this is saying take the derivative of the first, which I'll call du, the derivative of u, times you multiply it by the second, which is v, plus you want to take the derivative of the second, which is the derivative of v, which we'll call dv, times the original first, so times u. And we can look at this and say, okay, now suppose I was to take the integral of what I just did, right? So I can take the integral of the derivative of u times v with respect to x, and that should be equal to the antiderivative of this. Now I'm going to write this as v du, right? So equals the integral of v du, right? So v times the derivative of u, plus the integral of this piece I'll write as u dv. And on this, on this left side, we know that the integral of the derivative of u times v, right, should be just uv, right? When you take the integral of the derivative, you just get the original function out. So this goes back to being u times v, right? Or uv could be the other way of writing it. And this is equal to the integral of v du plus the integral of u dv. And what I'm going to do is I'm going to isolate one of these integrals here. Now the way we typically do this is I'm going to isolate the integral of the u dv. So I'm going to subtract off the integral of v du from each side. So minus the integral of v du. Now when I do that, on the left side here I have uv minus the integral of v du is equal to the integral of, remember these canceled, so it's the integral of u dv. And this actually gives us our integration by parts formula. I'll write it in the way you'll more typically see it, which is the integral of u dv coming first. So the formula that we use for integration by parts is the integral of u dv equals, and it equals what's on this left side, so it equals u times v minus the integral of v du. So, that's how we get the formula. Let's talk about what it really means. What we do at the beginning of our integration by parts, when we do it, we have a product. We're going to let u be represented by one of the functions, and then dv represent everything else that's left in the integral. And when we do that, then we can find other parts, meaning du and v, to fill in the rest of this. And we'll do it through and do it in an example. I think it's the easiest way to see it. But you should memorize this formula. It's the integral of u dv equals uv minus the integral of v du. The one thing that's important to remember here is that this is not a u substitution. These are kind of placeholders for where you're going to put functions in. So let's say, for example, we had this here. So in this example, I'll say we have the integral of x times e to the x dx. Now in the last section we talked about, we had a product of functions. We said, maybe we want to try a u substitution. And if you were to try a u substitution, just to kind of, remember what we did, we said, okay, I want to get into one of three different forms, one of them being e to the u power, if I saw an e in here. So you might think to yourself, well, I'll let u equal x, and then if I was doing u substitution, then du would equal just 1 dx, or just dx. Well, that would give us e to the u here, subbing in u, but then x dx, we don't have an x dx here. You can't create an x dx. You can't just put u into here, because then you still have u e to the u du, and it'll be the same exact integral. So substitution does not work here, right? But if you saw these all at the same time, you might want to try substitution first. So substitution doesn't work, so we're going to try what we call integration by parts. I'll use IBP for short, for integration by parts. And the way you want to try integration by parts is you want to pick one of your functions to be u, and then you're going to let dv be whatever's left over. And we'll talk about how to pick this more in a minute, but in this example I'll pick it for us. So there's two functions here, there's x and there's e to the x. Those are the two functions being multiplied. And the first thing you want to do is pick u. I'm going to pick u to equal just the function x. That means that dv is everything else that I have left over. So we pick u to equal x, dv is going to be equal to everything else in here. So if I pick this part x to be u, the rest of it, including the dx, ends up being the dv. What I'm really doing is just going back to the first page, is I'm trying to make it this form, the integral of u dv. So I'm picking u, the rest of it has to be dv, including the part that has the dx in it. So dv is going to equal e to the x dx. Looking at this formula here, right, I'm trying to fill in. We start with the integral of u dv. It's equal to uv minus the integral of v du. So what pieces do I need? Well, I need this piece. I've got u and I've got dv. That's just me just describing this side. This is actually what this is, the integral of u dv. The right side, though, we need u times v. Well, I have u, I need to find v, and then the integral of v du. Well, again, we have to find v, and I also have to find du. Well, how do you find them? Well, you find them from what you labeled these. So if I let u equal x, then you take the derivative of this to get du. Right? So going down this way, you're taking the derivative. So what's the derivative of x? Well, it's 1 dx. And from here, you've got dv. I'm trying to find v from there. Well, how do I get v from dv? Well, you want to integrate this side. So you want to integrate dv. Well, what's the integral of e to the x dx? Well, it's just e to the x. And we don't put plus c in here. We'll use that later on when we actually finish the integral. So now I have the pieces I need, and I'm going to substitute in. So when I say the integral of u dv, I'm really saying this is my integral, the x e to the x dx. So I'm really just saying here's my original problem. The integral of x e to the x dx is equal to u times v. So if you set it up the same way I did, u times v will always be going down this cross. So u times v is x times e to the x. And we're going to actually use x and e to the x. So this is just our formula to use for our placeholders, but we're really going to substitute in with the rest of it. So we have x times e to the x minus the integral of v du. Well, what's v? V is going to be e to the x. Du is 1 dx. Make sure you put the dx here, right? When you take the derivative, it's with respect to x. So it's 1 dx, which I'll just write as 1 dx for now so you see it. But 1 times dx is just dx. So if you're looking for your direct comparison, this part here is the u dv. This is the u times v minus the integral of this is v and this is du. Now once we've done this, what we're really going to do is we're going to simplify the right side. The left side is the original problem, so it's really just a way of setting it up so you have placeholders here. So this is the original problem. You're not going to do anything with the left side. We have x e to the x. That stays x e to the x. It's not an integral anymore. It's outside of the integral. You leave it alone. Minus, this is the integral of e to the x dx, just simplifying that. And we'll evaluate it. So we have x e to the x minus the integral of e to the x. So what's the integral of e to the x? Well, it's just e to the x. So we just write e to the x. And then since I'm done taking the integral, make sure you put plus c at the end. And so your answer is x times e to the x minus e to the x plus c. This is the antiderivative of x e to the x dx, our original problem. The integration by parts gave us a way of setting this up so we could find the integral. You couldn't integrate right away because we had a product, but we did know a way to get to what would work for the antiderivative. It actually, what it does is it makes an integral that's in a simpler form so that you know how to take the antiderivative of that, even though we didn't know how to take the antiderivative of the original. So that's the the process behind it. Let's talk about how you pick u, because to pick u is really part of the key to all of this is how you pick u. So to pick u, maybe I'll write it right here, just be a space for it. All right, so to pick u, use the following. order. All right, so first, if you see any logs, you'll pick those first. You'll let u equal any log that you see in the problem. If there are no logs, the next thing you want to pick u to be is any polynomial. All right, now polynomials include just, single terms, right? Those are monomials, but something like x in the last problem. And then if there are no logs or polynomials, then you'll let u equal exponentials. So this is the priority, right? So to pick u is use the following order. Maybe I'll put to prioritize, because this is the priority. So are there any logs in this original problem when we looked at it? No. The next thing we should look for are the polynomials. Were there polynomials? Yes, x was the polynomial, so I picked u to equal x. Right? Because remember, I said polynomials include monomials. So we let u equal x, and then everything else automatically becomes dv. Now, if there was no x in here, then you could use the exponential. But remember, exponentials are last on our priority, so it's unlikely that you'll use u to equal the exponential. And the main reason that is because it's easier for us to integrate exponentials, and it's harder for us to integrate logs. So that's why we use the order we do. So the order prioritized is logs, polynomials, and exponentials. Once you pick u, everything else becomes dv. So let's do some examples here. All right, so for this example here, let's take the integral of x times the natural log of x dx. Now, when I give you this integral, the first thing you should think to yourself is, okay, I have a product there, x times ln of x. Maybe a u substitution will work, what we learned in the last section. But if I did a u substitution, you would let u equal natural log of x, most likely, because we don't know how to take the antiderivative of that. But then du would equal natural log of x, the derivative of that is 1 over x dx. Well, I would need to replace an x dx. I can't make an x dx out of this. This is 1 over x dx. So you can't use a u substitution. You should check that first, and that's why I'm showing you this stuff. So if u substitution doesn't work, then we'll do integration by parts. And integration by parts, sometimes it's helpful to write out the formula. The integral of u dv is equal to u times v minus the integral of v du. And I'm going to keep writing it out so you don't forget what the formula is. And what you really want to do is remember, this left side of the formula is really the original problem. You're just picking out whatever you want u to be. So if I pick u, right, that's your first step. Follow our priority. So to pick u, our priority says start with logs. So are there any logs in the problem? Well, yes there is, right? We got natural log of x. So I'm going to let u equal the ln of x. So that's u, so then everything else has to be dv to fill this in. So dv is equal to, right, so ln of x, when we picked it, was what u, so x dx, all of this is going to be dv. So we just write it down as x dx. This is not a u substitution, these are placeholders. We actually don't ever integrate u or v in terms of the variable u or v. Right, they're placeholders for functions. And then remember what we said here. Now I need to be able to fill in the rest of this formula. So for u, I use that to find du. I take the derivative. So du, the derivative of natural log of x, well, it's the derivative of ln x. Well, it's 1 over x. And then make sure you write dx because you took the derivative with respect to x. The dv, we integrate to find v because those are the pieces we need, du and v. We don't have those yet. So to find v, we take the integral of x dx. The integral of x with respect to x is what that really means, would be x to the, remember you add 1 to the exponent and divide by that same new exponent, so x to the second over 2. Now remember, we did this because we're trying to fill in for this form. So now I've got the pieces I need, and now I'm ready to actually write out the integral. So I have this integral of x ln of x dx, right? That's the u dv part, and I'll write it out just so you see it, x ln of x dx. All right, and we're going to follow along with our formula here. So we have, this is the u dv, it's equal to u times v, so it's this times this. So we would have, it's equal to natural log of x times x squared over 2. This is uv, that's this part right here. And I always think of it as going down this cross if you write it in the same order I did. All right, and then minus the integral of v du, just going across this. So that would be x squared over 2 times 1 over x dx. So remember, we're doing this so we can simplify this integral into something that we might be able to integrate. All right, so we're just following the form. Making sure you understand, right? This is our u, this is our v, this is our v, this is du. All right, so I'm just following along with the formula above. And then we simplify. Simplifying this, natural log of x times x squared over 2, well, that's just going to be x squared over 2 times ln x. Typically you'll see log written at the end of it. It's okay if you left it in that order though. Minus this integral. Before you integrate this, I would recommend simplifying what you have. So this is the integral of, let's take a look. X squared over x makes that just x, right? This will cancel. The 1 over 2, the 1/2, you could factor to the front, and then make sure you still have dx, because it's with respect to x. And then what we're going to do is we're going to take this integral and simplify it. So you can't have any antiderivatives left in your problem, or any integrals left in your problem. You have to evaluate them and find the antiderivative. So you got x squared over 2 times natural log of x minus 1/2. What's the integral of x? Well, it's x to the second power over 2, right? Add 1 to the power, divide by that same new power. And then you can put plus c once you don't have any integrals left in your problem. And then simplifying, we end up with x squared over 2 ln x minus, this ends up being 1 times x squared is x squared over 2 times 2 is 4, so x squared over 4. And then plus c, and this would be the antiderivative of x ln x. So integration by parts gives us a way to simplify, so we have something that we know how to integrate in our second step. Now when we did this, a lot of times that integral you took there will be the same integration you did up here. Not always, but a lot of the times it will be, because we're simplifying it down using this integration by parts. Let's take a look at another one. Just similar but slightly different. So in this example here, we have the integral of ln of x dx. So remember what you're doing, right? This, natural log of x dx, might not look like a product of functions. It's really just one function. Natural log of x you're taking the antiderivative of. But we don't know how to take the antiderivative of natural log of x. And, we said, you might want to let u equal ln x if you're doing a u substitution. But if u equals the natural log of x, then du would equal 1 over x, and 1 over x dx, and I don't have a 1 over x in this, so there's no way to replace it. So you could use integration by parts on this to see if it would work. Remember how integration by parts works. The first thing you want to do is pick u. All right, so if we pick u, well, u would be equal to, following our priority, all right, first thing is log, so I'm going to let u equal ln of x. Well, then everything else, remember, has to be dv. Well, what's dv? In this case, dv, the only thing that's left is dx. And I'll write it as 1 dx here, just so you understand that really it's times 1, right? So times 1 dx needs to be in there. Once you have that, remember how our formula works, right? It's the integral of u dv, that's the original problem, is equal to, we do u times v minus the integral of v du. That's the formula. Now, if I do this, right, you got u equals ln x, you take the derivative of u, right? You have u, you want to find du. What's the derivative of natural log of x? Well, it's 1 over x dx, make sure you put dx after it because it's with respect to x. And then from dv, you want to find v because we need it in our formula. So you take the integral of dv, the integral of 1 over x, or 1 dx, right? So the integral of 1 dx, the integral of 1 is going to just become x. And then, you know, you don't put a plus c here because this is not going to actually be the end of the integral. So we've got du, we've got v, so now we're ready to substitute in. Remember, the integral of u dv is just the left side of the problem, right? So this is the integral of ln x dx. It's actually not part of your answer, it's just me showing you that this is just placeholders for this. And then you want to do u times v. Now, I've said this before, but it's kind of, if you write it in the same order I do, it's kind of thinking of like going down this cross. U times v, we have natural log of x times x, which I'll write as x times ln x, like that. You know, I'm changing the order on it, but multiplication can be written in either order because it's commutative. Minus the integral of v du. Well, what's v? V is x. What's du? Du is 1 over x dx, right? So that's really what I have here. Right, that's the v du. We're going to simplify this. X ln x stays x times ln x. Minus this integral, well, the x's are going to cancel, so it's really the integral of just 1 dx, or you could just say it as the integral of dx. Well, how does that integrate? That integrates as x ln x stays the same, minus the integral of 1 dx is just x, and then we put plus c because now I finished taking all my integrals. So the antiderivative of natural log of x dx is equal to x times the natural log of x minus x plus c, right? So we took that antiderivative there. So integration by parts, you know, is helpful when you have a product, but also if you have a function that, you know, you're not really sure about. Remember, the other function could always be, the dv part could always just be 1 dx like we had here. Because really we only had the integral of a single function here. Let's take a look at a few more. If I was to do this integral here, so for example, if I took the integral of 3x times e to the 3x power dx. So we have a product. All right, you might want to try u substitution like we did in the previous section. If you did u substitution, you'd probably let u equal 3x, but then du would be just 3 dx, and you have to replace this x in here as well, so u substitution won't work on this. So we have a product of functions. We should try integration by parts. When I try integration by parts, remember the first thing you want to do is to pick u. So if I pick u, here I'll let u equal, well, what's my priority say? My priority says I pick u based off of the following order, right? Logs, then polynomials, then exponentials. Well, are there any logs here? There aren't, so there are no logs. Are there any polynomials? Well, yes, the 3x counts as a polynomial, so the 3x is how I'm picking u. So u is going to equal 3x. Now remember, once you've picked u, everything else, right, the rest of it automatically becomes dv. All right, so dv is equal to e to the 3x dx, and make sure you include the dx in there. Now once you've done that, remember what we're doing. We take the derivative of u to get du, and the derivative of u, derivative of 3x, is going to be 3 dx. And we've got dv, so we want to try to find v from there, so we integrate this. The integral of e to the 3x dx, remember how this works. The integral for e to the 3x will be e to the 3x over whatever was in front of x, so over 3, whatever that constant was in front of x. And then now we're ready to use our integration by parts formula. Remember what the formula was. The formula was the integral of u dv, which is what we call the original one, is equal to uv minus the integral of v du. So on the left side, remember, I'm not doing anything, I'm just rewriting the original problem just so you understand that's what it is. So the integral of 3x e to the 3x dx, right, is equal to, and then we're going to follow through and find out what the antiderivative is. Well, if I'm doing u times v going down this way, I have 3x times e to the 3x over 3, that's the uv part, minus the integral of v du. Well, v is the e to the 3x over 3, du is times 3 dx. Alright, so this part here is the du, this part's the v, so minus the integral of v du. We're filling into here, right? So it's not a substitution, it's really just using these u's and v's as placeholders for the functions. And then remember, I'm simplifying this. So we got 3x times e to the 3x over 3. The 3's will cancel here. So I have x e to the 3x minus, here I have the integral, the 3's are going to cancel here. So I really have the integral of just e to the 3x dx. And now I want to evaluate this. X e to the 3x stays x e to the 3x minus the integral of e to the 3x. Well, that's e to the 3x over 3. Remember, it's e is the exact same antiderivative for e to a power that's a constant times x divided by whatever that coefficient of x was. And then plus c, because now we've taken our integral and we're done with that. So we have it. As I mentioned earlier, a lot of times this integral here will be the same thing that you integrated up here. Not always, but a lot of times it will be, so you can refer back if you're not sure. The reason this is the antiderivative of e to the 3x, remember, is that was from kind of undoing the chain rule. You actually could show it by using u substitution now that we've learned it, but it's one of those ones that you should know and have memorized. So this is the antiderivative of the integral of 3x e to the 3x dx. Let's look at a couple more. If I had this one here, if I said I want to take the integral of x squared e to the negative x dx. Again, we have a product, and when you have a product, you might want to try u substitution first, the product of functions here. If you did try u substitution, you might want to let u equal negative x, because you want to get e to the u form. But then the derivative of that du would just be negative dx. It doesn't help you with the x squared. Additionally, sometimes people might think, oh, let u equal x squared if you're trying to do a u substitution, but then du would give you 2x dx, and you can't replace the x and the e that way, so it wouldn't work. So if substitution doesn't work, that tells you try integration by parts. And the first thing we do is pick u. This is important. So when you pick u, we're following our priority. Logs, are there any logs in this problem? Well, no. Are there any polynomials? Yes, the x squared. So the x squared is how I'm picking u. Alright, so the x squared is u. So u equals x squared. Remember what that means. That means dv is everything else. Alright, so dv is equal to the e to the negative x dx. Alright, so this is dv. E to the negative x dx. And then remember what we do. We want to find du from u. So du is the derivative of u, so that'll be 2x dx. And then from dv you want to find the antiderivative, right? Because you want to find v. So we take the antiderivative of e to the negative x dx, the antiderivative of e to the negative x dx. If you're not sure, remember the integral of e to the negative x dx. Similar to what I just did in the last problem, this will be e to the negative x over a negative 1 plus c, because negative 1 is the coefficient of x on that exponent. So in that case, this actually just ends up equaling negative e to the negative x, right, if I was just to write that out. So v is going to be negative e to the negative x, right? That's the integral of e to the negative x. We don't put the plus c on this part because, you know, we haven't done the full integration yet. So remember the formula we're substituting in for integration by parts. The integral of u dv is equal to u times v minus the integral of v du. Substituting in here, remember the left side, the u dv, is what you started with. It's the original problem. You're not really going to do anything much with that, at least not most of the time, equals x squared e to the negative x dx, but you should have it shown there so you know that you have it. It's equal to, here we've got u times v. What's u times v? Well, it's x squared times negative e to the negative x minus the integral of v du. Well, what's v du? You have negative x, or negative e to the negative x times du, which we've got as 2x dx. Okay, let's simplify this. Simplifying this, we're left with this equals negative x squared e to the negative x. Just multiplying those together, putting the negative in front. Here I've got a negative, but I can factor out this negative, so it's going to be positive in front of the integral. And then the 2 can come out as a constant, so positive 2. And then you've got what's left inside here. You can't bring the x out. It's not a constant. It has a variable of x in it. E to the negative x also has to stay because it still has an x in it. So this is the integral of x e to the negative x dx. And okay, now that we're here, we want to integrate this. Now, typically when we do this, we integrate this and we get something that's in an easier form to use. But the integral of x e to the negative x is still the product of functions, so I can't take the antiderivative right away. So, you know, sometimes people get thrown off by this, but from this part here, you have to do integration by parts again, because that doesn't integrate just yet. You know, as it is, x e to the negative x, you can't take the integral of each piece. Sometimes people try to do that. Remember, as a product, you can't just take the antiderivative of each function in there. You have to actually use either a u substitution if that works, or integration by parts, which we're doing now. So this is integration by parts again. And the first thing you do, just like before, pick u. To pick u, I'm going to let u equal, remember how it works, our priority. We got logs, then polynomials, then exponentials. Well, are there any logs? No. Are there any polynomials? Yes, in this case, polynomial is x. So x is going to be what u equals. So u equals x. And remember, dv is everything else. So the rest of this, e to the negative x dx, is going to be the dv. So this is equal to e to the negative x dx. And then what you're doing with it, remember, you're taking the derivative of u to get du, so that derivative of x is just 1 dx. Make sure you write dx there, you need it. All right, because with respect to x. The integral of dv, right, which is v, the antiderivative of e to the negative x, well, it's the same one we did up top, right? It's the exact same one we did earlier. So this ends up being negative e to the negative x. Remember, don't put a plus c there because we're not done integrating yet. So from this, you know, we work down here. We're going to replace this integral, right? So this whole integral is what we did integration by parts on again. The 2's in front of it, so it's going to get multiplied through. This negative x squared e to the negative x is going to stay. So when we write this out, right, negative x squared e to the negative x stays. We have plus 2. And then I'm going to put this in brackets because now I'm doing this integration by parts here. 2 multiplies to all of it in the next step. So we have 2 times, and then when we do this, what do we've got? We've got u, so I'm not going to write out the whole formula again, we'll just follow the formula, right? So we got uv, right? So uv would be x times negative e to the negative x, right? So this is the uv part, right? And then minus, we want the integral of v du. Well, what's v du? Well, that's negative e to the negative x times 1 dx. Just to make sure you see it, right? This is v, this is du. So we're following our integration by parts again. It's really the same formula. And now we're going to simplify all of this. All right, so simplifying this, I have negative x squared e to the negative x. That doesn't change. Plus, we've got 2 in front. Maybe I'll keep the 2 in front for now. In the brackets, x times negative e to the negative x is negative x e to the negative x. Minus here, right, because that's from the formula, but then we got a negative inside of here. So factor out a negative 1, and negative times that makes this a positive. The integral of, and this will just be e to the negative x dx now. All right, and now we're going to be ready to integrate this part. All right, so now we're going to integrate that. The integral of e to the negative x, this is one that we can actually do. So looking at this, you know, we've got negative x squared e to the negative x plus 2 times, in the brackets, negative x e to the negative x. We know how to integrate e to the negative x. The integral of e to the negative x is going to be, so this is plus, and then e to the negative x, integrating that, it's the same one we did up here. It's actually, you know, the third time we're doing it in this problem, will end up being negative e to the negative x. All right, and then at the end of all this, since I've already taken all the integrals, I can put plus c. You don't have to put the plus c on the inside of this, because when you distribute through, it'll still be a constant, so we just call that constant c at the end. Last thing we'll do is distribute this 2 through, make sure we get the correct sign. So we got this negative x squared e to the negative x. A positive 2 times a negative makes this negative 2x e to the negative x. A positive 2 times a negative e to the negative x makes this negative 2e to the negative x, and then we have plus c at the end, and that will be it. So in this example, we had to use integration by parts twice. You know, students typically don't like that, but it's actually no different than what, you know, we did earlier. It's just that when you did your integration by parts, what you got in here was something that was still a product of functions, so you had to do integration by parts again. You don't necessarily have to show the whole formula here. I just wanted to make sure you saw how it happened, right? When you do integration by parts, make sure that 2 was factored out to the front. If you don't have that factored out to the front, you'll accidentally only put it with the first term and not with the rest of the integral, so that's important too. Let's take a look at just a couple more. If I said to evaluate this one, so for example, if I had the integral of x plus 4 times natural log of x dx. All right, you might want to pause it and try this one on your own. So when I look at this, first off, it's a product of functions. I'm going to try to use either a u substitution or integration by parts. A u substitution really won't help me much here. If I let u equal natural log of x, du is 1 over x, and that doesn't replace the x plus 4 dx. So we're going to try integration by parts. And the first thing we always do is pick u. To pick u, I'm going to let u equal what we need in terms of our priority. So our priorities say what? First thing to look at is logs. Are there any logs in this problem? Nope. All right, so first thing, are there any logs in this problem? Right, those are our priorities there. Well, yes, natural log of x, so we're going to use u equals natural log of x. And then remember, everything else, right? So if this is u, everything else becomes dv. So dv is going to be equal to, we've got the x plus 4, make sure you have that in parentheses like I have written it, and then dx, make sure you have the dx with it as well, right? So that whole part is dv. Everything else that's left over here automatically becomes dv. And once you've done that, now you're going to look for, when you have u, you take the derivative of u to get du. The derivative of natural log of x is 1 over x dx. Make sure you put the dx in there, because with respect to x. The dv, you want to get v from there by taking the antiderivative, right? The antiderivative, or the integral of x plus 4, well, the antiderivative of x is x squared over 2, add 1 to the power, divide by that power, plus the antiderivative of 4 is 4x. And now we're ready to substitute into our formula. Remember, the formula is this, right? It's the integral of u dv is equal to u times v minus the integral of v du. Substituting into this, remember the integral of u dv is really just what we call the original problem. So this is x plus 4 times ln x dx, right? This is u dv. Remember, these are placeholders. And it's equal to uv. When I say uv here, u times v, I think of it as just going down this cross, u times v. So it's ln x times the x squared over 2 plus 4x. So it's natural log of x, right, times, in parentheses here, x squared over 2 plus 4x. That's the uv part, minus the integral of v du I kind of think of as going across this way. If you want to remember it just by how you're moving for the multiplications, as long as you set it up in the correct order, this will always work. So we would have x squared over 2 plus 4x, that's v, times du, so times 1 over x dx. And now what we'll do is we'll simplify this. For the first part, ln of x can get distributed into this. So you have x squared over 2 times natural log of x plus 4x times natural log of x minus here, you can't factor any constants out to the front, so be careful not to try to factor 1 over x out. It's not a constant because it has a variable. But what you can do is simplify this. 1 over x getting distributed into this simplifies what you have. So minus the integral of 1 over x times the x squared over 2. That'll just, x squared and x will cancel to an x over 2. Plus 4x times the 1 over x. The x's cancel, so plus 4. And then we're taking the antiderivative of that with respect to x. Make sure you still have that dx in there. And then we'll integrate this, leaving these other terms as is. So we got x squared over 2 natural log of x plus 4x natural log of x minus, now remember this minus is in front of all of it, so you want brackets around this when you take the antiderivative. X over 2, the 1/2, right, that over 2 part will stay the same. So it's really, 1/2 and then x to the second power over 2, right? Add 1 to the power, divide by the power. This first 1/2 is that 2 in the denominator is like a 1/2 in front of it. Plus the antiderivative of 4 will be 4x. You can close those brackets and then put a big plus c at the end. Remember that constant is including everything that you would have gotten from the entire integration. So that's plus c at the end for the constants just being added together. And then simplifying this, distributing this negative through, we have x squared over 2 natural log of x plus 4x natural log of x minus, so a negative times a positive makes this a negative 1/2 times the x squared over 2 is x squared over 4. And then you've got a negative times a positive makes this a negative 4x. And then we've got plus c. And you can leave it like that. These aren't like terms. So that will stay as is. So that's the antiderivative of x plus 4 times natural log of x dx. So yeah, use integration by parts. Make sure you follow your priority. We'll just do one more here that shows, how to evaluate if you have limits of integration. And I'll do it on a new page. So if we had limits of integration on this, it's still the same process. If I said to evaluate, and I have the integral from 1 to 4 of x to the third times natural log of x dx. Right, so I want to take that integral. It's got, limits of integration, so it's a definite integral, meaning at the end we should get some numerical value. But the first thing you want to do when you integrate is, take a look at what you're trying to integrate in here. And in this case, I have a product of functions. If I have a product of functions, right, I should try to either use a U substitution or an integration by parts. A U substitution is usually your first line of defense, but if I let u equal the natural log of x, du equals 1 over x dx, I'm not going to be able to replace the x to the third dx. So a U sub wouldn't work here. So we try integration by parts, and to do that we pick u. To pick u in this case, remember our priority was logs, then polynomials, then exponentials. So you start by saying, are there any logs? Well, in this case, yeah, there is, natural log of x. So you let that be u. So u equals natural log of x. And remember, if u equals this, then dv is everything else. Remember, these are placeholders, u and dv. So dv is everything else. So dv is equal to x to the third dx. Remember how we use these, right? When we have u, we want the derivative of u to get, so du, and du is equal to the derivative of natural log of x, which is 1 over x dx. From dv, we want to find v. Remember, that's the antiderivative of this. So we take this as be x to the, add 1 to the power, so x to the fourth divided by 4. same new power. And you're going to do what you normally would do. So now we're going to rewrite this using our integration by parts formula. The integration by parts formula, remember, is the integral of u dv equals u times v minus the integral of v du. Remember, the left side is actually just what your original function is called. So integral of u dv is what we have up here, right? This is the integral of u dv. So it's the integral from 1 to 4 of x to the third ln of x dx. That's just the left side, is what it's called. And that's going to be equal to substituting in u times v, so going down this. So u times v is natural log of x times x to the fourth over 4. I'm going to write it as x to the fourth over 4 times ln x. That's how you typically would see it written. The last thing I'm doing that's different here, because I have limits of integration from 1 to 4, I'm going to put limits of integration on this from 1 to 4, because it's like we integrated that first part, right? There's no integral symbol on there. You need to evaluate it from 1 to 4 as you would for your normal limits of integration. Minus the integral, again, because we have a definite integral, I'm going to put the limits of integration on here from 1 to 4, and then it's v du. Well, v du is x to the fourth over 4, that's v, times du is 1 over x dx. Make sure you have that dx in there, you need it. And we will simplify. So I'm going to keep this as x to the fourth over 4 natural log of x, and we're evaluating it from 1 to 4. Now, you could just start evaluating this now. I kind of like to do it all at the same time, so I'm going to leave it there. Minus, simplifying this part, the 1/4 can be factored to the front. We've got the integral from 1 to 4 of x to the 4 divided by x is just going to be x to the third dx. And now we'll take the antiderivative of this piece. So we have the integral, or we have, sorry, x to the fourth over 4, natural log of x, being evaluated from 1 to 4. We'll do that in a minute. Minus 1/4. What's the antiderivative of x to the third? Well, that's x to the fourth over 4. Add 1 to the exponent, divide by that same exponent. And then, again, you're going to put the limits of integration on here from 1 to 4, because now you're taking the antiderivative. Do not put plus c at the end. For a definite integral, remember, we don't put plus c for the unknown constant. Now we're ready to substitute in for each of these. In this first one, I will substitute in 4 first, right, the upper limit. So we do 4 to the fourth over 4 times the natural log of 4, minus, we're going to sub in 1, so we'd have 1 to the fourth over 4 times natural log of 1. Minus here, I have 1/4 on the outside of this. I'm going to substitute in 4 first, so I have 4 to the fourth over 4, minus substituting in 1 to the fourth over 4. All right, this is just, following what we normally would do. Substituting in the upper limit, subtracting off the lower limit. Same thing here. Substituting in the upper limit, subtracting off the lower limit. And then we simplify. So 4 to the fourth over 4 is really 4 to the third, so that's 64. Natural log of 4 will stay natural log of 4. Minus, we got 1 to the fourth, which is 1 over 4, but then natural log of 1, remember, that goes to 0, so this whole term is 0, because natural log of 1 is 0. Minus, we have 1/4 times inside of here, 4 to the fourth over 4 is really 4 to the third power, which is 64, minus 1 to the fourth over 4. Remember, 1 to the fourth, make sure that's 1 over 4. Don't put a 4 up there. Sometimes people make that mistake. And then we'll distribute in, right? So we'll distribute this negative 1/4 through. So I have 64 natural log of 4 minus 1/4 times 64 makes us minus 16. Negative times a negative makes us a positive 1/4 at the end here. And then the last thing you want to do is combine these like terms. 64 ln 4 is the exact value there. I'm not going to do anything with that. I'll keep it as 64 ln 4. Negative 16, if I wanted to write it as fourths, make sure, oh, there's an error here. Sorry, negative 1/4 times negative 1/4 is going to be a positive 1/16. Sorry about that. Right, so 1/4 times 1/4 gives us a positive 1/16. So then to combine these like terms, what I'm really doing is I need a common denominator of 16. So this will be minus, well, 16 over 1 equals what over 16? Well, 1 times 16 got me 16, so 16 times 16 will give me 256 plus 1 over 16. And then this will be equal to, combining these like terms, I have 64 ln 4, that'll stay, Negative 256 plus 1 is negative 255 over 16. This is the exact answer. All right, so make sure you realize that's the exact answer. If you did an approximation, you know, I would only ask for that specifically. So if I don't say give me an approximation, or if it's not an applied problem, you should leave the answer in exact form, because that's the exact answer for the integral of, going back up here, right, from 1 to 4 of x to the third times natural log of x dx. When you use integration by parts, when you have a definite integral, make sure you put those limits on that first piece. Sometimes people leave it off by mistake, but you need the limits of integration there, as well as on your second integral, and then evaluate them. At the end of the problem, it should all be numerical. You shouldn't have any variables left, because then you wouldn't have evaluated it completely. So hopefully this helps in understanding integration by parts. Remember, you're using this when you have a product of functions inside of your integral. You also use U substitution for that, so it's important to know the difference. When you did U substitution in the previous section, you know, we did that because it worked out nicely. When you found du, you could replace the rest of the variables in the integral. You use integration by parts when you're actually not able to replace the rest of it using a U substitution. In integration by parts, the u's and the v's, right, are placeholders for functions, and you actually just replace them. You're not actually integrating the u or the v in terms of what you're using in the problem, right? They're placeholders as you're doing it. So hopefully this helps.